Okay, this is a recording for part 2 of our notes for Thursday, 2/28, while people are taking tests. So this will be some examples of using the law of cosines when we either have 3 sides or 2 sides and the included angle. And I will put up this other slide that I've put up in the past. We already did that deriving of the equation over there, but I do have this here because sometimes I like to just kind of remind you that if I know like these sides are 5, 6, and 7, then when I'm trying to find the angle, three angles, oh, I want to always find the largest angle first, and that's not an issue if if you use the law of cosines to find all 3 angles, but if you then defer to the law of sines, then it's always going to give you an acute angle when you use the law of sines, whether the actual angle is acute or obtuse. So when you're using the law of cosines, a nice rule of thumb is to find the largest angle first. And so here's our first problem. And in case I forget to say that, I have it right on my slides. Note, when given all 3 sides, find the largest angle first. So here's my 3 sides. They're 8 feet, 14 feet, and 19 feet. And I have to find all 3 angles. So I'm going to find the largest angle first. So that's the angle that is across from a segment AC, which is 19 feet, the largest side. And so I'm going to write my version of that. Cosine B equals A squared plus C squared minus B squared all over 2AC. And kind of just, you're going to want to remember this pattern. And just a reminder to you, I'll use yellow and then get rid of it, that when you're using this side that is opposite the angle, you only use that side one time. So I kind of keep that in my head, and then I know the 2 sides that I know here that are making that angle, I use those at the beginning, A squared plus C squared, and then in the denominator as A times C. So just some little, hints as we go, because we should be able to apply this to any picture as we go. And there we go. So now I just will plug things in, and a lot of times I just go right to B equals and find the inverse cosine. B equals the inverse cosine of, and now I'll just plug those in. A, which is 8 squared, plus C, 14 squared, minus 19 squared, all over 2 times 8 times 14. And one of the big things is these are a little challenging to type in a calculator. So when you go inverse cosine, you either get that first parenthesis or you have to type it in, and then that whole numerator has to be in a parentheses, and then a division sign, and then this whole denominator has to be in a parentheses, and then just good form to close that big parenthesis as you go. So if you want to pause this a moment and just try that before you look at the answer, that might be a good idea, just to kind of make sure. So B is equal to, so if you want to pause it now. But B is equal to 116.80 degrees, and I'm just rounding to 2 decimal places. Now, you can either go through that exact same process to find A and C, and using the law of cosines, and then there's no issues with that as you go. Or if you want, now you can defer to the law of sines and then the 180 minus the sum of the 2 angles. So whatever you do is fine with me, but just make sure that you show your work so that I can know, because sometimes things don't 100% add up to 180 degrees all the way, and sometimes that is unavoidable. But I will label this as 116.40 on there, and then I can defer to the law of sines just because, you know, it's a little easier typing in things like that. And so I'm going to say that 19 over the sine of 116.40 is equal to, and I'll just find angle A next, 8 over the sine of A. Cross multiplying, I get sine A equals 8 sine 116.40 divided by 19. And then A equals the inverse sine of 8 sine 116.40 divided by 19. And again, if you want to try that, go ahead and pause. Otherwise, I will just be showing you the answer. And so for that one, A is approximately 22.08 degrees. So once I have the two angles like that, and you know, so if I use the law of cosines for each of them, you know, they may or may not add to 180 depending on how I round, or if, you know, I did the next one. But if I use the fact that they add up to 180, then they will. So I can take 180 minus the 116.80 plus 22.08, or subtracting both of those, and then I get that C is equal to, or approximately equal to, 41.12 degrees. And so then there's our three angles for that triangle. Anytime you have all three sides, you can find all three angles. And I just model using several rules. If you want to use the law of cosines for every one, it will work out. And then this next slide, oops, I thought I had gotten rid of those. This next slide just kind of reminds you that cosine theta is greater than 0 from 0 to 90, but it's less than 0 from 90 to 180. So that'll give you the acute angle. And so it is wise to find the largest angle first, because then if you defer to the law of sines, it's always going to give you an acute angle. So just be aware of that as you go. So then I also want to make sure that we go over at least one that has the other version of the law of cosines. So for this one, I know two sides and the included angle. So I know this side, I know that side, and here's my included angle. So for that one, I'm going to find the side opposite that angle first, opposite that 25-degree angle. And so I just have to do what I can do. So keep in the back of your mind that there are some, I'm not necessarily finding the largest side first. So I have an angle that's going to be, has a possibility of being obtuse. So I have to kind of decide how I'm going to do that after I find this missing side. So I'm going to use the version that says a squared equals b squared plus c squared minus 2bc cosine, oops, sometimes I have trouble writing BC cosine, cosine capital A. And again, just notice this is a squared, this is angle A, and those are across from each other. So then I like to just change it into A is the big square root of b squared plus c squared minus 2bc cosine A. This is a nice just plug and chug problem as we go through. So now I just plug it in and kind of chug and I can get it. So this one's very nice to. So then putting that in, we get 9 squared plus 12 squared minus 2 times 9 times 12 cosine of 25 degrees. And really this one is very easy because we can just plug that in our calculator. If you want to pause this and do that, that would be great. Otherwise, I will show you the answer. So A is approximately, and I'm rounding lengths to the nearest hundredth. 1/4, which is 2 decimal places, and angles to the nearest tenth, which will be 1 decimal place. And so if you're ready, here comes the answer. 5.41 meters for that one. So now I'm going to just notice something, and that is that I have not found the largest angle. And so the easiest way to kind of not have issues, and there are other ways to do this as well, but the easiest way to not have issues is to find angle C next because it's opposite the largest side. And if I defer back to the law of, or stay with the law of cosines, instead of deferring to the law of sines, it'll be, I'll get the right one for sure. So capital C equals the inverse cosine of a squared plus b squared minus c squared all over 2ab. Oops. And again, the typing in of this is kind of the challenging part. And so C is going to equal the inverse cosine of 9 squared plus 5.41 squared minus 12 squared all over 2 times 9 times 5.41. And again, trying to type that in is a little bit challenging as we go. And so take a moment, and when you get that, you can check your answer. If you need to pause it to try that, it's 110.3 degrees. If you do it that way, then to find that third angle, you can just use the sum of the angles of a triangle equals 180. So then to get B, we can just take, B is approximately equal to 180 minus the 110.3 degrees minus the given angle, which is 25 degrees. So B is approximately 44.7 degrees. So your angles are here, and that side I can just barely see is right here. So there's one other problem that I'll put up, and if you want to try it, you can. It's what we'll start with going over tomorrow. So if you want to get some practice at it, you'll have seen it. And so it's an application problem. And here it is. It's number 3. The pitcher's mound on a women's softball field is 43 feet from home plate, and the distance between the bases is 60 feet. As shown in figure 6.9, the pitcher's mound is not halfway between home plate and second base, so be aware of that. You don't want to use SOHCAHTOA right triangle trig. How far is the pitcher's mound from first base? Kind of doing this mathematically. So I'll leave that picture with you, and you can try that if you want, and then we'll validate or go over it tomorrow.